So a galvanic cell, fancy word for a battery, also called a voltaic cell at times, also called an electrochemical cell or an electrolytic cell, all these different names, whatever, right? I don't care. They all have slightly different meanings. It's fine. In a galvanic cell, and remember, you are going to have to draw these. We always have two compartments, which I like to pictorially represent as a beaker. Tomorrow you'll be using well plates. And in each one of these beakers, you have to have a solution. And then we have to have something make contact with the solution. So that's going to be my electrode. So I'm going to have an electrode in here and an electrode in here. And the electrodes get connected doop, 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 with a wire. Cool. And then remember, because we want the electrons to go from left to right, if we hook the battery up like this, it would not run. Okay, or it would run for a millisecond and then it would stop. Here's why. If electrons are leaving this beaker would be losing negative charge. So this would become positively charged. And if electrons are entering this beaker, then this beaker would become negatively charged. And that's called static electricity, right? There's a separation of charges. Unfavorable can't do it. So in order to prevent that separation of charges, we use a thing called a salt bridge. And in that salt bridge, we like to usually use potassium nitrate. That's the salt you'll be using in your salt bridge tomorrow. And what happens here, the anion from the salt bridge comes over here, which is why we call this part of the battery the anode. And the cation from the salt bridge comes over here, which is why we call this part of the battery the cathode. So cations go here, anions go here. You can literally draw what I just did without even looking at the problem. In fact, I didn't even give you a problem yet, right? But this is like when you get a galvanic cell problem, you can get some points, man. Even if you do it completely backwards, you should be able to get some points. You can all draw this, memorize this, right? Okay, beaker, beaker, electrode, electrode, connect them with a wire, salt bridge, anode, cathode. Great. You got like 5 out of 10 points right there. You even do it. Okay, so that's nice. This is our generic drawing of a galvanic cell. Now what I want to do, I want to give you a redox reaction, okay? And I want to fill in the blanks. Now, what are the blanks? There's 4 blanks, okay? You got to label this electrode. You got to label what's in solution here. You got to label this electrode, and you got to label what's in solution here. So what do we need? Well, we need the oxidation half reaction to be taking place over here. This is where the oxidation half reaction, where we lose, remember oil rig, oxidation is loss. This is where we lose electrons. The electrons get lost and they come over here. And then we need the reduction, the gaining of electrons to be happening over here, right? So when I give you this reaction here in a moment and I want you to label boom, 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 you need to figure out who's getting oxidized, who's getting reduced, right? Because the oxidation needs to happen over here and the reduction needs to happen over here. Here we go. I'm just going to make one up. Let's do, oh, man, let's do, take a look at that. Not a balanced redox reaction. It actually doesn't have to be balanced for drawing galvanic cells. It's pretty sweet. If it bothers you, we pop a 2 there and a 2 there. Now it's balanced, and you don't have to be bothered anymore. I want you to fill in the blanks. Fill in those 4 blanks. And we'll talk about the right answer here in a second. All right, here we go. The oxidation half reaction is the lithium half reaction. So you want to build this electrode out of lithium. And you want that electrode, as the battery runs, is going to dissolve and it's going to produce lithium plus 1 cations in there. In a moment, we're going to talk about standard conditions. In fact, in order for the battery to run under standard conditions, you actually need to start with a 1 molar concentration of lithium ions in there even before the reaction begins. And then it's going to dissolve and produce more of them. This is my reduction half reaction. So in solution, we need the zinc plus 2 ions. That's what's going to receive the electrons, and then it's going to deposit as zinc on the surface. So we make that electrode out of zinc. And in a moment, we'll talk about standard conditions. You actually have to start with a 1 molar concentration of zinc ions in there in order for it to be under standard conditions. So cool. I love it. Awesome. We're actually going to save this and we're going to use it as our first reaction to predict the standard reduction potential. So here is our standard reduction potential table. We're going to talk about how to use this here right now to predict the voltage of batteries. What the heck is this thing, right? What is going on here? What is this giant chart? Well, let's talk about this chart. First thing I want to draw your attention to is the fact that these are all reductions, okay? And in fact, I'll zoom in a little more. Pick any reaction, okay? Every single one of these reactions is only a half a reaction. And in every single one of these reactions, everything is gaining electrons, right? Copper 2 plus gains an electron, goes to copper plus 1. You know, iron plus 3 gains 3 electrons, goes to iron. Nickel plus 2 gains 2 electrons, goes to nickel. Zinc plus 2 gains 2 electrons, goes to zinc. We're going to need that one in a moment. Okay, and they're all reduction half reactions. So this tells you the voltage associated with each one of these reduction events. Okay, so if lead plus 2 gains 2 electrons to make lead, that has a voltage of negative 0.13 associated with it. You'll notice that in the middle is the standard hydrogen electrode, and every scale, I've said it a bunch of times, I'll say it again, every scale has to have a reference point. It's got to have a standard, and hydrogen plus 2 hydrogen cations gaining 2 electrons to make hydrogen gas, that is what we call a voltage of 0. That is our standard. And if your voltage is above that, you have a positive voltage. And if your voltage is below that, you have a negative voltage. Now, here's the problem. If I want to use that chart to predict the voltage of, say, this battery, we have an issue. One thing is indeed being reduced. Zinc is being reduced. It's gaining 2 electrons to go, zinc 2 plus gaining 2 electrons to go to zinc. That is a reduction. We can find that in the chart as is. But we got a problem. The other part of the reaction, lithium going to lithium plus 1, that's an oxidation. And that chart is only reduction values. So what do? Here's what you do. Your oxidation half reaction, you just flip the sign of the voltage. Okay, so here's what we're going to do. Okay, because that reaction would be running backwards. If it's a negative 0.5 volts for reduction, it would be a positive 0.5 volts for oxidation. So the standard reduction potential table has chosen to only provide reduction values because all you do is if you have an oxidation event, you just flip the sign of the voltage. Let's write the 2 half reactions down so that we can see what's going on here. Here's our first half reaction. Lithium goes to lithium plus 1, and then I'm going to add that electron on there. And then the second half reaction is zinc plus 2 electrons goes to zinc. Okay, we're going to pop that bad boy on there. Cool. So we are going to be able to find this half reaction as is. You're going to find that in the table because it's a reduction. So let's just find that one, see what the voltage associated with that is. So zinc plus 2 electrons goes to zinc. That is a negative 0.76 volts. And you can see it is exactly as written right here, negative 0.76 volts. So what I'm going to do is I'm going to write that down. That is a negative 0.76 volts, negative 0.76 volts. Cool. And now we're going to find the lithium half reaction. But the problem with the lithium half reactions is it's going to be backwards. Whoops. Come on, Zoom, get this thing out of the way. We have lithium goes to lithium plus 1 plus an electron. We have this direction. So what do? Well, your oxidation half reactions, you're going to change the sign or flip the sign of the voltage. Since this is a negative 3.04 volts, we're going to flip that and make it a positive 3.04 volts. And now it's literally this easy to get the voltage of the battery. You just add them up. So we're going to take 3.04 volts minus 0.76 or plus a negative 0.76, and that'll give us the voltage of the battery. That is a 2.28 volt battery. If you made a battery where we separated lithium from zinc plus 2 cations, that battery would pull a voltage of 2.28 volts. So put that in perspective, your dry cell batteries, your AAAs, AA's, D batteries, whatever, they're 1.5 volts. Okay, so this would be a pretty high voltage battery, or higher voltage than your typical. Obviously you can link them in series and add them together and all that stuff. I want you to practice that. Okay, so I'm going to draw another reaction up here. Okay, and I want you, okay, to draw the galvanic cell and predict the voltage. All right, I want you to draw the galvanic cell for this battery, and then we'll try to get that voltage. Okay, go ahead. All right. So keep on going. In fact, if you already have it drawn, if you want to try to figure out the voltage, that's cool. That's what we're going to do next. Cool. So hopefully you have lead electrode dissolving into lead plus 2, copper plus 2, grabbing these electrons that come over and depositing on the surface of that electrode. So you may as well just make it out of copper. So now, how do we do this? Well, you're going to find this half reaction, and you're going to need to be careful because there's a bunch of coppers in that table. If you started looking, then you know what I'm talking about. Okay, but you're going to find this one as written. Copper plus 2. Copper plus 2 electrons goes to copper. We're going to find that one. It's going to take a little bit of effort, but we're going to find it. This one you're not going to find as written. You're going to find the reverse. So here we have lead dissolving into lead plus 2 electrons. We're going to find that one in reverse. Okay, so here we go. Let's find that copper one first, and you got to be really careful. Like, oh my goodness, there are so many of these things, right? We got copper gaining 1 electron. Nope, that's copper plus 1. That ain't it. Down here, we got copper plus 2, but it's only gaining 1 electron. That ain't it. You want this one right here, folks. Copper plus 2 electrons goes got positive 0.34 volts. That's the one you want. So I'm going to write that down. This has a voltage of 0.34 volts. Now, the lead half reaction, we're going to have to switch. So we're going to be looking for it, but it's going to be backwards. If you scour the table, right here is the lead half reaction. But we actually have this thing flipped, folks. It's going this way. So this becomes a positive 0.13 volts. So that's a positive 0.13 volts. Now you just add it up, 0.34 plus 0.134, that's positive 0.47 volts, right? Positive 0.47 volts.